Okay, yeah, this is usually how it is. File, files, insert. Okay. Everyone's done with the tutoring survey? Okay. Any questions from last session? You have your homework 8 due tonight, and as I mentioned, you don't have the traditional midterm for this class, but I'm going to post quiz 3. So initially I wanted to post it today, but since quiz is not due the Wednesday after the break, I'm going to post it later, so I'll give you more time to study too. And I'm going to bring to class some sample questions, so you have the chance to just complete some questions before answering quiz questions. And the quiz questions would be similar to the handouts that I bring to the class. So, and for that, I'm not going to grade those. So I don't want to create confusion. I'm going to bring some extra questions for you. And for those, you're welcome to just consult with each other, solve it with each other, because I'm not going to grade those. But they're going to provide to prepare you for the quiz 3. Okay? Good. Any questions, comments? So what subjects do you want me to have like more questions on, or what subjects are you struggling most? Is it like naming compounds? Is it like pi sigma bonds? Anything specific that's pi sigma bonds? So anything else? Covalent bonds, different type of intermolecular bonds. What's that?
Naming the triple and double bonds.
Okay, naming triple, double bonds. What else?
Reaction mechanism.
Reaction mechanism, okay. What else? Okay, so I have like some specific examples on those, and try to provide also some sort of study guide. Okay, so if we're good with the survey, let me start with the lecture today. So when I went through the materials, I realized that I need to explain in much more detail about thermodynamics before talking about equilibrium. So this is what I'm going to do today. So in general, when we're dealing with reactions, we have two concepts. One is thermodynamic, the other is kinetic. And we mentioned these briefly during the last session. So thermodynamics tells us whether or not a reaction occurs. Or if you remember, based on the reaction that we had before, or like the generic reactions, we said AA plus BB in equilibrium with CC plus DD. And that meant that both reactants can react with each other and then produce the products, and also the products can react back to each other again and then produce the reactants. Okay? So can you tell me, the guy with the hat? Okay, can you tell me how can I write the equilibrium constant?
Was it a to the a power times b to the b power over c to the c power d to the d power?
Okay.
Or was it flipped like numerator denominator?
So we have like c to the power of c. So we have like first products, exactly. And d to the power of d divided by a to the power of a multiplied by b to the power of b. Excellent. And so are we good with these two lines that I added here? Good. Any questions about that? And I'm going to revisit that in the next slides too. But this was kind of like review of what we learned before. In general, we have two concepts. One is enthalpy, the other is entropy. And when we have like this equation written as such, we have like some quantity named Gibbs free energy. So you may ask, what is enthalpy and what is entropy? So enthalpy is basically your reaction energy. But if you have a reaction occurring in constant pressure, your reaction energy is called enthalpy of reaction or reaction enthalpy. Okay? And this is basically what we showed before, and we talked about having like endothermic reaction or exothermic reaction. Do you remember what was exothermic reaction? Exactly. It produces heat. It releases heat. So you have like some reaction written like AA plus BB, and then it gives CC plus DD plus heat. It's like combustion, that it generates energy, right? On the other hand, you might have a reaction like AA plus BB plus heat gives CC plus DD. And this reaction is endothermic, right? Because it absorbs heat from surrounding. So enthalpy of reaction can be positive or negative. Can anyone tell me, based on what I wrote here, or based off of exothermic, endothermic reactions, which one is delta H less than 0? Exothermic, exactly. Because it releases heat, right? It's as if it produces heat. What about delta H greater than 0? Endothermic, exactly. It absorbs heat. It's kind of like here. Okay? So are we good with enthalpy? Any questions? We also have another quantity named entropy. And entropy is associated with the state of disorder, randomness, or uncertainty. And in general, in reactions, we want to have, or like, as I mentioned before, if we have like some materials or substances, they want to reach lower energy state. And this is how nature works. If something has really high energy, they want to release that energy to reach to a lower energy state. For entropy is reverse. The particles, the reactants, the substances, they want to gain more entropy. They want to have more randomness. That's why if you have like a container that is like filled with gas and then you open it, they distribute into the room because they want to move more. They want to have like more randomness. Okay? Does that make sense? Okay. And this is like the, as I said, if we have like enthalpy of reaction minus T delta S. And delta S is the difference in entropy. Delta H is difference in enthalpy. And T is like temperature. And the symbol delta always means difference, remember? So difference in entropy and difference in enthalpy, and T is temperature, which has like the unit of Kelvin. It's like absolute temperature. And depending on the sign of, yes, question?
Oh, you can finish.
Yeah, no.
Okay, so if delta means like the difference in something, and enthalpy is like the constant pressure, why does H have?
So what is constant pressure?
Like the enthalpy, it says it's at a constant pressure.
No. Yes, at constant pressure, reaction energy is called enthalpy of reaction. It means that if you're carrying out a reaction in laboratory, your pressure is the same. The pressure is not changing. So for instance, it's 1 atmosphere. Or like depending on reaction conditions, your pressure is constant. But if all of these, basically delta H, T delta S, and delta G, all of them are energy. They have units of energy. Does that make sense?
Yeah.
Great question. Any other questions? Okay. So depending on the sign of delta G, we know whether a reaction occurs or not. And that is, I guess I just add another slide. Okay. If delta G is less than 0, it's negative, it means that the reaction occurs. So thermodynamically is favorable, we say. Thermodynamically, it is favorable. But if delta G is greater than 0, the reaction does not occur. So it's not thermodynamically, or I guess I can say it is not favorable thermodynamically. Any questions? Good? Now let's talk about entropy change more, because I think more of you heard of enthalpy before, or reaction energy, so it's like more tangible concept. But how many of you heard of entropy before? Okay, so not as few. But how can anyone know how can we discuss entropy in a reaction? So how do I know that what is the entropy change? So how do I know that entropy increases or decreases in a chemical reaction? If I give you a chemical reaction, how would you know that if entropy is increasing or decreasing?
Number of moles.
Exactly, number of moles. Yes. So one thing is number of moles, and as I wrote here, if you have like decrease in number of moles, you know that entropy decreases because the number of molecules basically is decreasing. And also reverse, if you have like increase the number of moles, means increase in entropy. And also if you have like multiple phases, so if you have liquid, solid, and gas, which one do you think has higher entropy? Gas, right? Because gas molecules can move more randomly, right? So they are like more disordered in a sense. But if you have like solid, the solid molecules, or like ions, depending on what we have, they are like more structured, right? So more structure is less entropy, okay? So now we want to solve some examples. So here in the first one, do you think the entropy is increases or decreases? So the girl with the glasses that you're on your phone, can you answer this question so I see if I'm teaching this well or not? So does entropy increases or decreases here? Why decreasing? Increase? So why is increasing? So the answer is correct, is increasing, but increasing. So we count the moles in the reaction, right? And to count the moles, we basically count the coefficients after balancing the equation. So this equation is already balanced, right? And do you remember how to balance equations?
Yeah.
How do we balance equations?
You gotta get the same number of elements on each.
Exactly. So we count number of elements on each side. We make sure that they are, the same. I guess I don't see any nitrogen here. So, that is interesting. So we have like 2Cr here, 2Cr here. We have like yeah, do you guys see what is wrong with this equation? What is it? Yeah, we have like, so probably, let me see if this is nitrogen. Does this solve it? So how many, doesn't quite solve it, does it?
There's 8 oxygen on the right and 7 on the left.
Uh-huh. Oh. Let me see what would be. Let me see if I type this correctly. I don't have this here. Okay, I'm going to look into this equation. So I have like nitrogen here on the left, but I don't have any nitrogen on the right. So I should look into the reaction to see what I wrote wrong here, okay? So that's why you should make sure the equation is balanced, because if it's not, anything else that I'm writing is garbage, because this reaction is not actually a valid reaction. Okay, but hypothetically, if this was a reaction and everything was correct, yes, the entropy was increasing because we have like more moles on the right side. But let's go to this example, the second one. So here, entropy, is it increasing or decreasing? So because we have like 2 plus 1, 3 moles. On the left, we have 2 moles on the right. And remember that we write, so these are states of your reactants or products. This is gas. You write L as liquid. Liquid. You have like S as solid, right? And then AQ as like aqueous. AQ, right? It's like basically dissolved in water. Okay? So what about here? So the equation is balanced. You should make sure it is balanced because this is the coefficients that we are counting. So you have like 1 mole on the reactant side, and then 1 plus 1, 2 moles on the right. So again, entropy is increasing, right? Increase in entropy. Okay?
So the middle one was decreasing though, right?
So this one is decreasing, exactly. So you have like 3 to 2. This is like decrease in entropy. So if the number of mole decreases, your entropy is decreasing. But remember, if you have this example before I realized this is not valid, but if you had let me have like a generic reaction. If you have like A solid gives B solid plus C liquid plus D gas. Or maybe I substitute the coefficients. You have like 1 here, 1 here. Like, imagine you have like, even if I have like 2 moles here, or like 2 moles here, what I'm trying to demonstrate is that if you have solid turns into gas or liquid, still, because you have gas and liquid, they have like much more entropy. Does that make sense? But I give you a question that is straightforward, because if number of moles increases, right, but you have like different states, it can be tricky because you should consider the effect of both, right? But remember that gases in general, they have much more entropy compared to liquids and solids. Any question? Okay. And this is basically the reaction that we wrote before, the generic reaction, and this is the equilibrium constant that your friend mentioned. And also, we have like basically delta G changes in Gibbs free energy equals delta H minus T delta S, and these small zeros that we write on top here, it shows a standard condition, which is depending on the reaction conditions, these are like tabulated in books. So basically standard conditions are like 25 centigrade degree, 1 atmosphere. So we have like tabulated data of H and S, basically enthalpy and entropy, and scientists or chemists tabulated data that what these numbers would be at 25 centigrade degree and 1 atmosphere, right? At like standard conditions. So this denotes standard condition. And delta H0 equals H minus H0. Delta S0 equals S minus S0. So if we define these as such, delta G0 equals G minus G0. So what that means is that in this equation that we just mentioned here, these ones are values that you read from like tables that they give you, or like you look up from the internet, or like these are tabulated, so you don't have to worry about them. These are like the same for the materials that you're working with. So these are like constant. Didn't mean to do that. Okay. But enthalpy and entropy is specific for the reaction that you're working with, right? And then if you have those numbers, you substitute them, and then you get delta G 0. Does that make sense? Again, these are like things that we agree how we do that. So a standard condition, we just define that. So you can also, depending on, what you define, you can also say that, okay, I want to have like my reference like 0 degrees centigrade, and then you tabulate your data based on that, and then you solve the question based on that. But this is like how chemists agree to do this, okay? So if you agree with the standard Gibbs free energy that I just explained, it happens that it has a relationship with the equilibrium constant that we talked about before, and I wrote here, which is negative of gas constant multiplied by temperature, which is like absolute temperature in Kelvin, multiply by ln, which is like natural logarithm of equilibrium constant. And R has like the value of 8.314 joule per mole per Kelvin, and then T is temperature in Kelvin. Any questions? Does this make sense? So I have the ln of x here to refresh your memory. So if this is like the y-axis, this is like x-axis, this is how natural logarithm of x looks like. And I guess the better demonstration is that this goes to 0. So if x goes to 0, your function goes to minus infinity. So that's what it means. Do you guys have you ever seen this? How many of you heard of natural logarithm before? Okay. So can anyone tell me when this function is 0, at what x? Exactly, right? You see when x equals 1, you go to your graph, and then you read the value, which is 0. Okay? Now let me write the equation again. So we had like delta G0 equals minus RT natural logarithm of delta, sorry, this should be K equilibrium. Okay. Okay. So based on this, can anyone tell me when, just looking at this graph and this equation, or just like before that, can anyone tell me when I said the reaction occurs based on delta G? Exactly, when delta G0 is negative, the reaction occurs based on what we agreed on, right? So now, looking at this expression here, can anyone tell me when that happens? Looking at this function, basically logarithm, natural logarithm of K equilibrium.
When KQ is greater than 1.
Exactly. And this is what I told you last class, remember? Then when K equilibrium is greater than 1, the reaction proceeds from left to right. It means that we have more products. So this is why that is. Does that make sense? So what about delta G0 greater than 0? When, based on what I just wrote, what do you think? When that would happen?
It's less than 1. K is less than 1.
Exactly. So last class I just wrote you the expression that K equilibrium equals, like if you have like A plus B, equilibrium with C plus D is like concentration of C to the power of C multiplied by a concentration of D to the power of D divided by A to the power of A multiplied by B to the power of B. And then I told you if K equilibrium greater than 1, the reaction goes left to right. If K equilibrium is less than 1, it goes right to left. Right to left. And I didn't tell you why. So this is the reason. Yes?
I have a question. Is the reaction the same, like if you had three different compounds and go each on the other side, you still kind of equate the same way? Like if you had 3 that you started with and they kind of combined these 2.
Exactly. I mean, this is a great question. So the question was that what about if I have like A plus B plus C in equilibrium with D plus E or like more. So the equilibrium constant would be, we write that in the same way that we say that concentration of products to the power of their coefficients divided by A to the power of A multiplied by B to the power of B multiplied by C to the power of C. So if you have like more reactants or more products, you do the same. Just remember, concentration of products to the power of their coefficients in a balanced chemical reaction divided by reactants. Great question. Any other questions? Yes.
Do you have another example of this?
Yes.
Different graph?
So what type of example you mean? So this is
Just like a different numbers, I guess.
okay. So I have a numerical example towards the end. Yes.
Oh.
Yeah. But the graph is just like the same.
Graph always like that?
For natural logarithm of x, basically this is always like this. Yes.
What would a question about this
So I just have the graph here so you know why. So if you see the graph, you know that, okay, at like x equals 1, or here in this case, when equilibrium constant is 1, delta G0 is 0, or when it's like more than 1, if I can regenerate this, the value here would be positive, right? So this value would be positive, and then delta G0 would be negative. Or, so it's kind of like just to understand this equation.
Just a visual, gotcha.
Yes.
Those questions would be based off.
No, I don't ask you the graph or like math specifically, but I kind of like want you guys to see that when equilibrium constant is less than 1, let me have like here another. So when it's less than 1, you see that the values are negative. So logarithm of k is negative, and negative multiplied, because t is always positive, because remember, this is like absolute temperature in Kelvin. So we don't have any negative Kelvin temperatures, right? Because the lowest temperature possible is 0. So this is always positive. This is like a constant, it's always positive. So if this is negative, negative multiplied by negative is positive. So that's why when K equilibrium is less than 1, your Gibbs free energy would be positive. So that's why basically these are happening. But as long as you just remember these, you're fine. I don't ask you the graph in the exam.
So
Yes.
the bottom reaction, the reaction doesn't occur on that one because it's.
Exactly. So that's why your reaction goes the other side here. So, yeah.
Okay, thank you.
Yeah, great question. Any other questions? Okay, so these are the things that you need to know. As I said, let me do the highlight as well. So this here, and then the equation, what it is, and then the most important things, these guys. But if you don't learn why these things happen, in the exam, when I tell you true or false, you may get it wrong because you didn't actually know how we get there. But if you remember the graph and then the math behind it, it's less likely that you made a mistake. You make a mistake. Okay. If no question, then we go to the next slide. So this is basically the summary of what I just wrote before. That if you have like the reaction listed as here, and then again remember this double-sided arrow, it means that reactants produce products, products produce reactants, and depending on the value of K equilibrium, you have the reaction going left to right or right to left. Okay? And just feel free to interrupt me at any time if you have any questions. So now let's have an example. So it says, a question asks, and I also have like resources here in case you want to go to the website, have like more examples, or like see this example that we solved here with more explanation. So it says calculate the equilibrium constant for the below reaction if we have like this much mole of carbon dioxide plus this much of hydrogen and this much mole of CO and this much of water vapor in 2-liter reaction vessel. And again, remember to first check if the equation is balanced. You have 1 carbon on the left, 1 carbon on the right. You have like 2 oxygen on the right, 2 on the left, and then H2 on the left and right. So the reaction is balanced. Okay. Can anyone?
Be balanced, or would you put a question where we have to balance it?
So I'll give you the balanced
Okay.
equation because that is not the focus on this class. So you're supposed to know how to balance chemical reactions, but this is not the focus of our class. But always make sure,
Okay.
in case I give you something like the previous example that something was wrong with it, you can tell me that this is wrong, So can anyone tell me how I can proceed with solving this question? Or what is the first thing you do? Usually,
Set up equilibrium
uh-huh.
formula.
Exactly. So usually we first write the formula to see what we should calculate, right? So can anyone tell me or help me to write this? What is equilibrium constant for this reaction?
0.0092.
Yes, but what is the, just like one step before?
Oh, like the C to the powers.
Uh-huh.
0.0092.
Uh-huh. But just like if I want to write the formula, right?
It's C to the powers.
Uh-huh. So concentration of CO to what power? 1, right? So remember, if you don't have any number here, sometimes the students tend to think it's 0. It's not 0 because you're seeing something, right? If it's 0, it's basically non-existent. So it's 1 when we don't write. So it would be concentration of CO to the power of 1 multiplied by, and I have like one student in my 101 class that they're like upset that I write like multiplication sign like this. They asked me to use dot. So whichever you're more comfortable, it doesn't matter. Or if you don't write anything, it means that multiplication, right? Like the formula that we write. So here would be concentration of H2O to the power of 1 divided by concentration of CO2 to the power of 1 multiplied by, exactly, right? And now that you wrote the formula, and I advise you to write the general equation so you don't make a mistake in the exam. And if our exam wasn't multiple choice question, I would ask you to write it because I would give credits for intermediate steps. But unfortunately or fortunately, I guess for me fortunately because it's less grading, but fortunately or unfortunately for you, that's not the case. So sometimes you know the question, you write everything wrong, you put it wrong in calculator and then lose 4 points in the exam. So that is unfortunate. Anyway, so how can I calculate concentration of CO?
0.1918.
Exactly. I go here, I say I have like this much of CO, right? So I write 0.0092 moles. You can just write moles or mole for brevity, I guess. Divided by volume, right, which is 2 liter. So this would be concentration of CO. Multiply by what about concentration of H2O?
0.0092.
Exactly. So write H2O with blue. Divided by 2 liter. Right? So you have like reaction, here reaction vessel, right? Or a reactor that it has like a confined size. It's 2 liter, right? And everything else that is being produced, and all of these are gases, so all of them have the same volume. So for that matter, you just divide the moles by volume. And then for CO2, you do very same thing. Here, 0.1918 mole divided by 2 liter multiplied by H2, which is 0.0908 mole divided by 2 liter. And sometimes the students just tend to put everything in calculator, but sometimes you can just like simplify this before doing that, right? So all these two, cancel out with each other, right? So you don't even have to, that would be one less step in the exam, right? So this would be 0.0092 multiplied by 0.0092, right? Because these are like the numerators, right? We would do this in our school. Basically, these numerators of the ratios that you wrote on the numerator of this ratio, bigger ratio, multiply by denominators of these, which is like 1, divided by 0.1918 multiplied by 0.0908. So now putting this in calculator is easier, But you can just kind of like put everything in calculator, whichever is more convenient for you. And when you do so, you get here 0.00486, which if you round it, it would be roughly 0.0049. And if you want to write the scientific notation, it would be like 4.9 multiplied by 10 to the power of minus 3. So what would be the unit for equilibrium constant? What is it? Moles per liter. Does anyone have any other ideas? Just moles. Any other ideas?
Isn't it unitless?
Exactly, it is unitless because you have like mole per liter multiplied by mole per liter divided by mole per liter multiplied by mole per liter. So these guys just cancel out, right? But that is just specific to this reaction that is unitless, right? Because when we write equilibrium constant, we have them to the power of their stoichiometric moles, right? The balanced chemical reaction. So if I have like 2A plus 3B gives like 2C plus 6D, for instance. Right? When you write these concentrations, you have concentration to the power of 2 multiplied by concentration of D to the power of 6 divided by concentration of A to the power of 2 multiplied by B to the power of 3. So if you just consider the units, so if I have like mole per liter to the power of 2 multiplied by mole per liter to the power of 6 divided by mole per liter to the power of 2 multiplied by mole per liter to the power of 3. So these two guys just cancel out, right? Because they're just the same. So it would be, do you remember working with powers? When you divide, they subtract, exactly. If the bases are the same, you just write one of them and then deduct these two numbers. So it would be mole per liter to the power of 3. So depending on coefficients that you have here, the unit for equilibrium constant would be different. In this very example that we wrote here, this is unitless. Does that make sense? Yeah.
Are you ever going to want us to convert moles to liters or like vice versa using like the Avogadro number?
So we're not using Avogadro number as of right now. But remember, so basically you cannot convert mole per mole to liter, you know. So when you want to convert units to each other, they should have the same nature. So we can convert moles to grams based on atomic mass unit, or we can convert liter to cubic centimeter or all that, right? But you cannot specifically, I mean, you can report that in one specific volume how many moles you have, so that is right. But specifically, if I tell you I have like 2 moles of a substance, I mean, that doesn't make sense to ask you what would be the volume, because you can have that much of substance in like in this room, or like in this university, or like depending on the volume that we're talking about. Does that make sense? Okay, great question. Any other questions? Okay, if no question. So this is basically the summary of like just what I told you before, but I wrote that here because I'm going to ask like true or false questions, or say which of the following statement is not correct, is correct. So I just wanted to emphasize that you should just like study this. And the other thing is that, as we said, I mean, your book just wrote the chemist's term for heat energy enthalpy, which is kind of bothersome to me, or like it's kind of like it's not completely correct, because we don't just call heat energy enthalpy if we have constant pressure in our reaction. We call heat energy enthalpy. So I just wanted to emphasize that, and based on what I had before. But in general, in exothermic reactions, we have evolution, I guess, of heat of energy, so release of heat. But in endothermic reactions, we have like absorption of heat. And if you have like, if I give you like the reaction diagram like here, and then here you have like your reactants, here you have like your products. If the energy state of products is lower, it means that your system has lost energy, so gave heat to the surrounding, and it has like lower energy right now. So delta H is negative, okay? And we have like the same thing for the opposite. If you have like your reactants and then your products, if products have like higher energy, it means that they gained some energy, right? So delta H would be positive. And again, you know, your book has like this K equilibrium greater than 1 and then less than 1 corresponding to delta G, delta H, but that is not quite right. These correspond to delta G. That if it's positive, it corresponds to K equilibrium less than 1 and then the same thing. So this is not quite accurate just for the reason that I mentioned. But your book just assumes that entropy doesn't change, so delta H and K have like relationships. So this is your attendance. And if you have any question with any part of the course, you know, never hesitate to reach out to me. And I keep trying to communicate that to my students, that I don't know, never be afraid or like ashamed to come to me and then ask for like questions or like for help if you're like struggling with the course, because that's the last thing I want. Or I don't want at all. Yes.